Hello, thank you for tuning in to Continental Controls and Design. My name is Lori Hines, and I'm going to be introducing you to our company and its disruptive electric motor technology. Continental Controls and Design, or CCD, is a Southern California corporation with a core focus on active control of wideband, high-power, density electric drives. Our technology arises from our many years of experience in high-performance drives and dynamic controls. CCD has over 25 years of experience. Across several contracts, we are currently helping the Air Force, NASA, and the Navy to improve electric drives for applications including propulsors for the X-57 electric aircraft demonstrator, self-starting capability for the E-2D aircraft, electromagnetic actuators for high-speed Navy surface craft, and extended endurance for multi-rotor UAVs. So who should listen to the rest of this presentation? Well, anyone who has a use or need for a drive in the size range from 1 to 100 pounds and would like to have the heat dissipation and weight of their motor. Even if your application currently uses hydraulic or pneumatic technology, this may be an opportunity to come away from the dark side and electrify to glean the clean green benefits. I will be giving you more details on our patent-pending technology, and while I present, perhaps you will want to start thinking about your applications and how you can benefit from better thermal, power, and weight specifications for your electric motor applications. Now I'm going to talk in more detail about the specific starter application for this SBIR contract, and then I'll circle back to the improved motor's wide range of potential applications. Over the past decades, the E-2 has been the quarterback for the Navy's carrier groups and gives the warfighter expanded battlespace awareness through advanced sensor fusion. All this, but the darn thing can't start itself. In fact, it's the last carrier aircraft dependent on a pneumatic hover cart to provide the requisite oomph for starting. This is, of course, a logistical burden, and it makes operation from remote airfields nearly impossible unless they happen to have a hover cart handy. The genesis of this SBIR topic was a 2016 Navy feasibility study for onboard starting of the E-2D Hawkeye. Onboard starting of the E-2D presents a unique set of challenges. Like a lot of other military aircraft, it is so heavily equipped that in its current state, it approaches its gross weight limit. However, other aircraft are able to carry an auxiliary power unit for onboard starting, but the E-2 cannot afford the extra space and weight. The E-2D has a maximum takeoff gross weight of 57,500 pounds, and it currently runs at about 56,890 pounds. The study authors deemed that the desired solution should have less than a 250-pound net weight gain, and they thought that a conventional electric motor solution would be too heavy at an estimated 500 pounds. That all changed when CCD presented its innovative electrical solution, which is nearly weight neutral after removing almost 200 pounds of unneeded pneumatic components. Our electric starter for the E-2 is similar to a car starter, but has about 100 times the power and runs 10 times as long. We believe this is the most powerful battery-powered aircraft turbine starter to date. Batteries are not new in aviation applications. You may have heard that the Boeing Dreamliner uses batteries, but they start an APU, which then bootstraps to provide the power to electrically start the main engines. The Navy already has large lithium batteries in F-35 aircraft deployed on aircraft carriers. The main components of our starting system are the battery pack, the inverter, and the motor. Under the SBIR, we didn't focus on revolutionary battery technologies since that industry is improving as fast as it can. Instead, our secret sauce is in the motor and inverter design. The original E-2 pneumatic starter didn't have any software or electronics on board since it was designed half-century ago. So now we can introduce a smarter, more modern paradigm with built-in diagnostics that improve functionality and maintenance, and at the same time, we eliminate the headaches of finding and using a ground-based hover cart. During the Phase 1 effort, feasibility simulations were performed to size the components. Follow-on efforts included testing of components and then complete subsystem testing. A development of this scale would normally include dynamometer testing, but we in the Navy were confident in our modeling, so after some COVID delays, we went straight to the engine test stand for a full-scale demonstration. We are now in the Phase 2 expansion stage to finalize ConOps and integration with the rest of the aircraft systems. Our ability to successfully go directly to the electric self-start demonstration shows that a SBIR vehicle can really get stuff done. In April 2021, our technical team traveled out to Naval Air Station Pax River, and after recovering from shipping damage, an amusing little aside being that apparently UPS Freight doesn't use those fragile handle with care stickers because they reserve the right to drop your crate from a height of 3 feet. So the electronics has seen some damage, but our team stayed up late that night, repaired it, and the next day they bolted it up to a T56A427 at the Outdoor Test Site Building 2376. The test motor was out of spec, yet our electric drive performed 6 successful starts on 6 attempts with no failures, including 3 consecutive starts without recharging the battery. On our last start, we demonstrated redundancy by enabling only 3 of the 4 quadrants of the motor and inverter. It started right up within the specified 1-minute start sequence. This table summarizes the advantages of our high power density drives. The first row describes the present application, the self-start system for the E-2D aircraft. The self-start solution removes the need for ground support equipment, which lowers cost, while allowing for remote airfield operation. This expanded mission flexibility will be a game changer for the warfighter. But now I'm going to jump to the third row, the battery. It is the heaviest component in the system, as batteries are going to be batteries. That said, the battery pack must be optimized for a combination of power density, energy density, and cycle life. Our custom battery management system tracks and reports the state of charge, current, and temperature of the series connected cells. As I said earlier, other Navy aircraft already use large lithium batteries aboard aircraft carriers, so we are working with the Navy on battery selection criteria to include logistics and safety. Back up to row 2 is our inverter with several hundred gallium nitride power switches. The parallel count is optimized for minimum total internal loss, increasing the efficiency from 98% to 99%. What, a 1% increase? That doesn't sound like a big change, but in fact, it has huge consequences. The 1% increase of efficiency halves the thermal load from 2% to 1% of the delivered energy, and most of the inverter weight is attributed to thermal management. So having the heat results in significant weight reduction and improved reliability. I won't bore you with a deep dive into EE design, but the engineers assure me that it's just physics. And what system designer doesn't need less heat, lower weight, and more reliability? So now down to row 4 shows our most significant innovation. The performance of all electric motors scales with the amount of copper packed inside. So it may sound hard to believe that even the best small motors, including the ones sent to Mars this year on the Ingenuity helicopter, don't even fill half of that available space. Wires are just really hard to pack efficiently. With power-dense electric machines, especially used in modern composite airframes, thermal management is often a major headache. The temperature rise is proportional to the volume fraction of air in insulation in the motor slots, and with our winding process, the air volume is drastically reduced. Our patent-pending winding process approaches complete fill, doubling the amount of copper in the stator slots. This increased fill halves the electrical resistance and copper loss, while simultaneously reducing the thermal resistance by a factor of 3 or more, due to what is called the inverse rule of mixtures. The increased thermal and electrical conductivities combine to reduce the internal temperature by 2 for the electrical resistance times 3 for the thermal resistance, which ends up reducing it by 6 times. The first transition target has been identified as the self-start system for the E2D, and our current effort involves integration concerning details such as installation locations, component positioning, cabling, ConOps, and environmental aspects, recharging and adding other operational modes such as engine cooldown, washing, and fire extinguishing, as these applications run for longer than the starting sequence and have a different torque speed profile. By now, you may have started thinking about your applications that could use a boost in efficiency and performance. Whether your application involves vapor cycle or HVAC systems, hydraulic pumps, propulsion for urban air mobility, or unmanned aerial vehicles, hybrids, or dynamic actuation for control surfaces, electric drives are the way of the future. Even a small increase in drive performance can have a significant positive effect on range and mission capability. I've told you that CCV has 25 years of experience helping the Air Force, NASA, and of course the Navy. If you need a modern electric drive from 1 to 100 pounds and would like to have the heat dissipation and weight of your motor, our technical team is ready to help you solve your problems using our patent-pending technology. This SBIR contract vehicle and our other contracts may give us ways to work with you to solve your problems. Transitioning the self-start capability to the fleet is a collaborative effort with the Navy, Northrop, and Rolls-Royce. So thanks for coming along and hearing about our advanced motor technology. Challenge us with a new or old application problem. Connect with us via video chat or the contact information here. Thanks again.